I'm now going to talk to you about a bit of history of electronic noses from sort of the earlier days to what's happening now, and how these electronic noses, which I'll explain what they are, can be used to try and diagnose illness. So first of all, just to let you know that anything you see or hear has been published. So I have publications I can send to people. I've published a number of books and so on. So there's no confidentiality. You can share whatever you hear today with whoever you want. So now into the talk. Here's a quick overview of my talk. First of all, I'm going to assume you don't know what an odor is. So just a few slides introducing odors, and then also a little bit about the human olfaction system, human olfactory system. I spent many years obviously working with biologists and medics and so on. Just a couple of slides on that. Then on to what an electronic nose is in terms of the definition, as you can see here. And then some of the desktop instruments commercially available today that you can go out and purchase. Then talk about the applications, in particular diagnosing diseases from cultures and swabs. Obviously, this is very topical with the issues with coronavirus and diseases. And then something that's very recent, which is the use of breath analysis. So I want to have a few slides about that. And then finally, I'll just sum up with somewhere where we're going in terms of perhaps robots, drones, smell communication, wearable devices, and mobile phones. So first of all, what are odors? Well, first of all, an odor or a smell is a molecule that you can smell, and it's usually a small polar light molecule. It has to be light, of course, because otherwise it wouldn't be airborne. So they have quite low molecular weights so that they can get into the air, into our noses, and be smelt. Typically they're polar, but they can also be non-polar as well. A polar just means it's got like an OH group on the end of it. It's got polarizability within it. And this particular molecule here is a carbon and an oxygen. It has a fruity smell, very simple molecule there. So electronic noses should be able to detect simple molecules that are odorant. It could be detecting a complex odor, and that's much more interesting. So when you have your coffee later on today, you'll be smelling coffee and you'll be tasting the coffee, and that's got tens to thousands of different molecules. I'll show you later on in a quick example of detecting coffee roasting levels. The olfactory threshold is typically parts per million to parts per billion. So when you smell something, it's in that sort of range. However, for some reason, we have adapted to some odors at very low levels. Don't ask me why, but grapefruit. So if you do like your grapefruit, we have one of the lowest olfactory thresholds for grapefruit. No idea why. It's not poisonous, and it has a very, very low level. So when you're thinking of smells and odors, you're probably thinking of wine and food and perfume and so on. And there are many things called like fragrance wheels. So we can then separate different smells by classifying them as oriental smell, a woody smell, a fresh note, or a floral note. So when you drink your wine, you might describe it as being aromatic, it might have a smell of grass in there, or more likely to be fruity if it's fresh, and then later on more woody smells if it's an older wine. The intensity is a non-linear scale, so when we smell more in a log scale than a linear scale. And different smells can be low or high, so something that you smell low can be pleasant, like urine, but when it's a higher smell, it's unpleasant, as you probably know. And we call those olfactory units olfs. And optical isomers can actually smell differently. So over here, you can have exactly the same molecular weight, but it can have a different smell if it's got a different optical isomer. So what is human olfaction? Well, the human olfactory system is quite a complicated engineering structure, and as engineers, we probably appreciate this. First of all, you've got fluid dynamics. So you sniff, and you have three turbinates within the nose, the lower, the middle, and the upper turbinate. And when you sniff, it's quite easy to sniff. And the reason is that 95% of the air doesn't go to the olfactory bulb, it bypasses and goes straight down your throat. And only about 4 or 5% of the air that you sniff in goes up to the olfactory bulb in this upper turbinate over here. It then diffuses and gets captured within a mucus layer, a sort of polar mucus layer that washes over the olfactory epithelium. And then within that epithelium are around 350 different olfactory binding proteins. And they're around then attached to those, about 100 million olfactory receptor cells. And then on top of that, there are other cells, mitral cells, and glomeruli nodes, about thousands of those, and then about 50,000 above that. So it's a very, very complicated AI system, plus a fluid dynamic system. And in fact, 3% of the human genome is involved with coding up for olfaction. And I think that is an indicator of how complex it is. Over here, I'm showing in the mucus region these receptors sitting in liquid phase over here. Now, the electronic nose concept has come around in the late 1980s, and the first companies emerged in the 1990s, and it's still an emerging market, probably worth over 100 million. People say it's larger than that. Hundreds of millions is the size of the market. So it is still a sort of niche market. So what is an electronic nose? Electronic nose, first of all, there's no standard for one. There is no definition. There's no standard for a smell. There's no standard for electronic nose. There's no standard databases. But we in the community have been trying to develop databases that people can use, and we are working with the IEEE on an official standard for these things, but there isn't one at the moment. So I published one a little controversially, perhaps, in 1994 in a paper which I entitled The Brief History of Electronic Noses. I was cribbing a certain other person who used the word a brief history. And how I defined it was as an instrument, electronic instrument, which comprises an array of electronic chemical sensors with partial specificity. That means they have overlapping sensitivity. They don't respond just to one odorant. And then you needed a pattern recognition system, and that would enable you to classify and recognize simple odors, that's a single odorant, or complex odor, which could be tens or hundreds of different odorants. And over here, I was showing you it electronically, an analog sensor, chemical sensor at the front end, and different sensors, pre-processing them, digitally processing them, an array processor, a pattern recognition, and then output. But this is my own definition that people do use, but as I said, there's no formal one. In terms of process overview, perhaps more processing, when you smell something, here's a pepperoni pizza, the sensors will respond to it. The array of sensors will produce a time-dependent signal. We generally pre-process that time-dependent to try and extract some sort of features from them that are independent of time. And then we use a pattern recognition method over here. And when we transform those into classification space or odor space. So over here, let's say we've had 3 different pizzas. This pizza is in this direction, this pizza is in this one is this one, and then the intensity of the pizza is along this line. But more importantly, as you go around it, we can separate out those 3 different odors in ideally a reduced dimensional space from the sensor array. So what about the limits of these instruments compared to the human nose? Well, the human nose is sitting over here between parts per million, parts per billion, if you're lucky down at parts per trillion. And the basic electronic nose that we've been working on start here, and then by improving them, we can get down from parts per million to parts per billion. So that's the sort of capability of an e-nose with, this is an SPME, which is solid phase microextraction, a little bit of pre-sampling method. Over here is a mass spectrometer that someone may be familiar with. And if we bolt on a GC mass spec for about £100,000, we can get down to parts per trillion, which is around 10 to minus 12 grams per milliliter of liquid. And over here is Fido the dog. So this is why we still use dogs to detect explosives, because they can go down to parts per quintillion, 1 part in 15, which is extremely low, as you can imagine. So what about desktop units? Well, for around 20,000 upwards, you can buy these commercial instruments. So the company I founded in 1993 is over here, Alphamos. It's a sort of market leader, and it still exists today. And over here, you can see an electronic nose, a headspace autosampler, and a computer. So it's a desktop-based unit. Over here is Agilent. they reconfigured one of their quadrupole mass spectrometers to make it into a sort of electronic nose. And down here, you can see Owlstone over here. If I just move that out of the way, and I'll say a little bit more, I'll give an example of it over here. But over here is the Owlstone Medical Breath Analyzer. Here's the breath unit. Here it is, that recently won the Roberts Award for Engineering, which is sponsored by your worshipful company of engineers as well. And that also is costing some money and doing very well. The sorts of sensors in there are very variable. So there are many electronic noses that have been reported using different principles. Some use conducting polymers with nanomaterials included. So it's a non-conducting polymer with carbon nanospheres. And as the smell goes in, it expands and the resistance goes up. And here's a 32 element array based on these conducting polymers. Here's another one, conducting polymer called Osmotec. The company is now called Genmark. In the early days, again, was making conducting polymers. But probably the most common is what we call metal oxide semiconducting gas sensors, another nanomaterial. I don't have time to go into all the materials and how they work, but basically it's another nanomaterial that its resistance changes when the smell hits the surface. But they're all non-selective. They're not biological things, they're repeatable sensors. Handheld units are over here, also on the market. I've worked with this company over here. I'm on the advisory board of Serrano Sciences in the early days. And this is a handheld polymer-based unit costing around $10,000 or 10,000 euros. This one over here is using surface acoustic wave devices. So you can buy these little VOC checkers that are on the market today. So what about applications of electronic noses? Well, in the early days, a lot of time and effort was spent detecting different cheeses, different foods, and different beverages. So over here, you can see, perhaps as you have your cheese board, you can recognize different cheeses. Well, here's the electronic nose with 32 sensors. This is what's called principal components analysis. So what we're doing is we're displaying in two dimensions, the 32-dimensional array, which shows that they're all quite correlated, which is why you can do this, showing it in just two correlated dimensions. And over here, you can see the different cheeses are nicely separated out. So you can classify Gruyere, different types of Gruyere even. So this one is quite close to this one because they're very similar cheese. Over here is a different sort of cheese. And let's hope we can distinguish it from water, which of course cheese is a lot of water and salt, and it's over here. So in the early days we were doing that. We have done coffees. So here's a showing you the molecular content of coffee, which has 670 different compounds within it, alcohols, aldehydes, ketones, acids, and so on. And over here, we were showing how you could measure the coffee roasting level for a company to control it using electronic nose. And as you burn off the alcohols and aldehydes and ketones and turn them to acids and esters and other different compounds, you can then change the smell, taste. And we were showing that you could use electronic nose to measure that. So now into sort of diagnostic in healthcare. So people have been very, very busy thinking, what can you do with electronic noses? And food is one area, pollution is another area, but a big area people are looking at now is personal well-being and healthcare. And I want to focus now on those particular aspects of it. So first of all, what could we do in terms of electronic nose to detect ear, nose and throat infections? So can we help doctors detect bacteria? So when we started off, I think as the first group to do it in the world, we looked at culturing infections. So now for centuries, Chinese doctors have used smell as a diagnostic. If you smell a patient's breath and you can smell something on it, like acetone, they probably got diabetes or maybe a liver infection, and the Chinese use smell. We don't do it in the West, but what we have looked at is trying to look at breath. I've looked at urine, I've looked at feces, skin, sweat, and so on. But to begin with, we swabbed patients like an ear or an eye infection, grew the culture, and then tried to identify it with an electronic nose. And we could do it rapidly within a few minutes once it had been cultured. But of course, it does take time to culture it. And so you can use a headspace of bacterial cultures to identify ear, nose and throat infections like E. coli or staph. And then the doctor can apply the right antibiotic, because otherwise they have to guess what's the most likely infection. Here's just one example, because we don't have a lot of time, of an eye infection. So we took patients with bad eyes. This is a beautiful eye, but they had mucus in their eye, they had an eye infection, and we swabbed those, grew the cultures, and compared them with known bacterial infections that we'd grown. We did it with a handheld unit, with a doctor, a local doctor, and we were able to then apply this technique. Here's the raw data you can see here for different bacteria that we've got in our database: E. coli, Staphylococcus aureus, Streptococcus pseudomonas, Pseudomonas aeruginosa, influenza, and so on. So these are all well-known bacteria, things that can occur, and we grew them at certain concentrations and to see how sensitive we were. And we were able to actually classify different bacteria using our electronic nose, again, just showing this simple principal component space, which isn't a proper pattern recognition method, but it just shows you we've got some separation, but it's not 100%. So the accuracy of these noses is not 100%, but typically around maybe 90%, in the 90s as a percentage point. So what about breath analysis? Now, all the excitement recently has been trying to use breath analysis. Very easy to do. You don't have to swab. You don't send it off to a lab. You don't have to wait. You just simply collect breath. Now, the reason the excitement of breath is that there are a lot of diseases that have been reported giving you elevated VOCs on the breath. So imagine if you've got neck cancer inside the neck, then the cancer will be producing gases, and that will show up in your lungs. If you have asthma, which is a lung disease, or a chronic pulmonary disease, it affects your VOCs in your lungs. Breast cancer is also reported, but I believe that's a small amount, and so on. Liver cancer produces certain chemical compounds, cirrhosis of the liver, hepatitis, diabetes is a big signal, inflammatory bowel disease comes through, and so on. So this is what's raised the excitement of many, many people. Now, don't go away thinking you can detect all these with an e-nose. You can't, but there have been reports of elevated VOCs, which show some excitement for this particular area. So let's just start off with some gaseous markers, which are quite easy to do. Carbon dioxide on the breath is usually between 3 and 4%. And if that's quite widely measured and shows you how efficient your metabolism, but it also is linked to obesity, and I've done some work on that. Carbon monoxide, assuming you're not a smoker, because if you do, you'll have elevated levels of carbon monoxide. You can see parts per million here of CO on the breath, which means we've got a chance of measuring asthmatic patients produce carbon monoxide, but so does COPD. It's interacting with the blood on the lungs and showing it up. Nitrous oxide on the breath is also another diagnostic biomarker for asthma, as is rhinitis, as you see, but here it's much lower levels. It's parts per billion level, which is more difficult to detect than parts per million, but still possible using our sensors. We can get down there. And cystic fibrosis as well. All these naturally occur on the breath, of course, at the ppb level, so you're looking at small increases in them on the breath. Hydrogen on the breath can mean diarrhea. I think you'd know if you had that anyway, but gastroenteritis, diseases, and so on. And methane on the breath is an indication of diverticulitis, a very painful blockage in your intestine, constipation, but also irritable bowel system, and then that's also at the ppm level. Other things at the ppb level, these are all biomarkers. I won't go through them in detail, but you can see there's a whole host of different chemicals. Isoprene is very commonly on the breath. Acetic acid, benzene's on the breath. Benzene also is in our air, and toluene and acetone. So you can see what people are trying to do, find the biomarkers, use electronic nose of some sort, and classify them. But what I'd like to say is in terms of breath analysis, it isn't easy. If you want to do, as we want to do, measure in real time, then the breath varies a lot. It's different flow rates. You have to teach people to breathe through it. It's humid, it's wet, it's a variable medium. And also you need to take the breath that's been near the blood, so you need to get a certain part of the breath. You throw away the first part and use the breath that's later on. So there's all sorts of complications to it. But we've been looking at VOCs on the breath, trying to do it in real time. In terms of where it's at the moment, famously, as you know, Alstone won an award because it's been doing breath analysis by engineering this quite complicated structure over here. So you breathe into this, stores them in these vials over here, and then you decant them to measure this technique over here, which is called ion mobility spectroscopy, completely different to the technology that I've been developing. What I'm trying to do is move away from this to making something much, much smaller. You breathe into this chamber, the sensors are in here, and then connected to the mobile phone and out. So let's just have a look. Here's a quick video here of a commercial sensor that we've been developing to measure VOCs on the breath, alcohol, and CO. And it's been commercialized by one of the spin-out companies. Over here, you can see the sensor is just here. You've got a number of sensors in here. All the rest is the electronics, and that's a plug-in to your mobile phone. It's a multi-gas sensor unit. You can see it will measure VOCs, ethanol, carbon monoxide that we've been developing. And here's a simple test. Now you can see how fast it is. This is real time. In a few seconds, it's showing it. You put another pulse, instantly, within a second, it's responding. And that's the sort of thing that we are trying to develop. In terms of what can we do now, and then finishing off with the future in a few minutes. So e-noses can help doctors diagnose from swabs and breath. And I think they are useful in terms of saying, is it a bacterial infection or a viral infection? So if you go to the doctor, he uses one of these, he could say, no, it's a virus, no point to use antibiotics, or he could say it's a bacteria. Similarly, with a fungal infection in the ear, he could discriminate those, and he should be able to get what sort of bacteria it is, and then we'll be able to do this. If you have a very strong biomarker like acetone for diabetes, NO for asthma, and CO, methane, again, we should be able to pick that up. However, it's not suitable for mass screening, and because the accuracy is only in the 90s, if we had, for instance, 50 COVID patients per 100,000, like it's circulating at the moment, we would detect 48 of them. But if we detected 100,000 people for mass screening, 5,000 would be false negatives. So unfortunately, you cause too many problems. If you go in suspecting it with the symptoms that different, it's a 95% accuracy. Lastly, just to look at what's the future capability. Well, we've been looking to put them on robots, drones, and make smart devices. So I won't go into the details, but we've been looking at blends of specific biomarkers. So in other words, insects detect not absolute concentrations, they look for ratios of existing chemical signatures within air from several kilometers away to find their food sources. So we've been developing electronic noses based on insects, in which we've been learning not the individual components, but the ratio of those components. And here we're using a very advanced deep AI olfactory. It's a model of the anterior lobe of an insect incorporated in analog VLSI, and then we've put it onto an FPGA, and these are sort of acoustic wave devices, which we published recently. So here the robots want to send a signal, pretending it's an insect, as a food source, and there's a robot. So how does this work? Here's a little video, hopefully I'm showing you, which will show you we'll inject 3 different ratios and send the information to a robot or insect to do different things. So the first smell is the right smell of the food or its mate, and we send it, it's just come out, and the robot is signaling. It's signaling, it's moving to the left. Maybe it doesn't like that smell, so it's not going to do anything. Okay. It's just signaling, moving to the left. We're now going to change the signal, and we're going to change just the ratio of those 2 chemicals, and then, I like that ratio of those 2 chemicals, and the insect is moving towards the source. Okay, and then we can do the same thing, keep repeating it, and it comes forward and it comes forward. And lastly, we're getting another, it doesn't like it, so it's backing off. We've got infochemical communication using e-noses. Right, last 2 slides. First of all, we've been making wearable devices to detect the smell of urine for a hospital for incontinent patients. This is a big issue. They wear pads, they break through, they want to know we can detect smell. And we're showing here the accuracy of the e-nose to differentiate between synthetic urine, ethyl acetate, ammonia, and acetone, which are all parts of smell. But interestingly, we got urine 100% correct. The And here is the sensors, 3 sensors, all in a device. So where's the future to sum up? Where are we going with e-noses? Well, we want to put them in phones. There are 1.2 billion phones sold last year. So could you imagine getting them in there? We've been working with Samsung and other companies. We could put them in wearable devices. They don't sell as many as those, perhaps 10 million a year. We're working with smart home companies. So we put our sensors in certain smart home devices, not Nest and Hive, but other ones. We'd like to see them in refrigerators, toilets, cookers. But the big question is, if we're going to put them in phones, they must only cost $2 each. So they want 250 million a year for $2 each. Smell phones are coming, but I would say slowly. So thank you very much, Master.